discuss the alkali earth metals, and you know that S block is constituted by two groups. One is the alkali earth metals and the other is the alkaline earth metals. In the last class, when we discussed the alkali earth metals, we primarily talked of lithium, sodium, potassium, rubidium, cesium and francium. In this we saw that francium is actually radioactive in nature, whereas the rest are considered to be more or less like metals. Why metals? Because the configuration for the alkali metals is NS2, is a NS1, sorry, it's primarily NS1. That is what we've understood. For hydrogen, when we did the hydrogen chemistry, we understood that when we are talking about the hydrogen chemistry, there was something that was related to alkali metals as well as it had similarities with halogen. Now when we started talking about now the S and P block chemistry is what is to be done. When we start talking about the periodic table and the groups in the periodic table, you know that essentially the properties which are there in one particular group are going to be more or less the same. Why? Because the outermost electronic configuration is the same, and you know if the outermost electronic configuration is the same, the participation in bonding would also be similar. Now here, because they have only one electron in the outermost shell, they are considered to be reducing in nature. Reducing in nature means that they can act as good reducing agents. And you know what is a reducing agent? जो दूसरों को reduce करता है और खुद oxidize हो जाता है. So all these metals you know are capable of getting oxidized to M plus an electron. This is the oxidation reaction you know. Now let us just quickly revise some of the important definitions and concepts which will help us do the alkaline earth metals quickly, which was left last time. We look into some specific compounds also for our alkaline earth metals. This is alkali which we covered last time. So here say some important concepts. I'll write down the term on the board and you try giving the definition. What is ionization energy? It is the energy required to remove an electron from an outermost shell. Very good. It is the energy required to remove an electron from the valence shell. Look up, there is no need to write right now. It is only a revision which is going on so that the next groups can be dealt with easily. Next, we also did talk about electron affinity or electron gain enthalpy. What was that? It was the energy released when an electron is added to the outermost shell. Very good. It is the energy released when an electron is added to the outermost shell. Then we talked of electronegativity. What is electronegativity? It is the tendency of an atom to gain electrons. Like for halogens, the configuration is Ns2, Np5. It has a tendency to gain an electron. So that is why you would say that that's electronegative. Electronegative का मतलब है जैसे if your halogen is present with any electropositive element, then it will have a tendency to pull the electron density towards itself. Now so that is why it will be said to be electronegative in nature. But the moment it takes the electron density completely, then you say that an electron is added to it, क्योंकि जो इलेक्ट्रॉन लेता है वो नेगेटिव हो जाता है और जो देता है वो पॉजिटिव हो जाता है, and this is going to be electropositive in nature. That means this involves Na को Na plus बनने के लिए क्या involve, what is it involving? Ionization energy. And X to become X minus is involving electron affinity because it is the energy released when an electron is added. So now you will say that here electron affinity is involved and this is your ionization energy after which is involved for the formation of Na plus. So now what we have is, now what we basically have in this particular case is that we can talk about this to be majorly electropositive in nature because it is very easy for them to donate an electron. Then what were the other parameters? If you talk about the size, you know on going from top to bottom, size increases, the rest of the properties generally decrease. Then we had seen that when you are talking about the S block elements, they can readily form their ionic radii. Let me just tell you, smaller the size of the ion, greater is the tendency with which it can get hydrated. Okay, I repeat, जितना छोटा आयन होगा उतनी ज़्यादा tendency होगी of the water molecules or the solvent molecules to hydrate it. So which will get the most hydrated according to that? Li plus. So the hydration energy is the energy which is like released when water is interacting with your ion. That thing is clear? So which will be the most solvated? Lithium. So hydration enthalpy will be the highest for and then it will go on decreasing accordingly. That is for the ions. Alright, what else? If now I talk of the formation of oxides, तो oxides हमें पता है कि ये अगर plus है, O is generally O2 minus. So general oxides that lithium forms is Li2O. ठीक है? The general oxide that sodium is able to form is that's peroxide, that is Na2O2, and the rest K, Rb and Cs are forming superoxides. इसकी हमने special property already redox में पढ़ी है कि जब हम Li की बात करते हैं, there O has an when I talk about the oxide of lithium, that there O has a -2 oxidation state. When I talk about a peroxide, O has a -1 oxidation state, and when I talk about the superoxides, there O has a -half oxidation state. Alright, so we had then, after checking up some of the properties of the alkali earth metals, we moved on to check some of the compounds of sodium, where we had studied about washing soda. Then we talked about the water was done in hydrogen chemistry. So we did talk about washing soda, we talked about sodium carbonate, which is like washing soda itself. We also did talk about other elements like sodium hydrogen carbonate, which is baking soda, sodium hydroxide. Now one method for the preparation of sodium hydroxide was by electrolysis. That electrolysis is carried out in a special cell which is known as Kastner-Kellner cell. So such kind of things only need to be brushed through. कि एक बार एक concept समझ में आ गया, the others then it can be applied to the rest as well. Alright, one more important thing that we did was like lithium, the very first element of each of the group, behaves a little, in fact it behaves very differently than the rest of the members of the group. What is the reason of that? What is the reason for that? When we talk about lithium or any other member, we see that here this is something which has non-availability of any d orbitals. Alright, the first element is the smallest in size. Alright, and then it shows relationship with the element which is positioned diagonally into the next group. Alright, and we saw that the next group for the alkaline earth metals is what? Beryllium, magnesium, calcium, strontium, barium, radium. Alright, so you have basically this as your second group. I hope you remember it by now. Alright, and I don't want to repeat that terminology that you have. So you know, this is actually beryllium, magnesium, calcium, strontium, barium and radium. Alright, now here in this case again similar things will now come up. Like first of all, we know that these are the elements. What is the outermost config? Now today we are going to lay emphasis on the alkaline earth metals. These are the alkaline earth metals. Now again, certain important things that you need to actually take a note of. On going from top to bottom, size will increase again. Why? Because each and every for each atom, now you have a shell getting added up, and so the size is generally increasing. Remember that with addition of shell and the number of electrons which are coming in, the nuclear charge is also increasing. Like for example, if this is 5, right? No, if this is 4, then this is 1s2 and 2s2, right? This is what it is. Then this will be 2s2, 2p6, 3s2, right? Now for this, what I want to tell you is that if number of electrons are increasing on by the addition of shells, remember that the nuclear charge is also increasing sufficiently, because the number of protons on the nucleus is equal to the number of electrons. So जितने electrons बाहर shell के through add हो रहे हैं, उतने ही protons हमारे nucleus पे भी हैं. So the nuclear charge is also increasing, which will tend to hold the electrons also tightly. But जब shells add होते हैं तो क्या होता है कि they actually provide shielding to the nucleus also. Just get it. Shielding in the sense that it will not allow nucleus to interact as much as it was possible because of repulsions that it will give to the other electrons. Like charges will repel each other. तो हम नीचे जाते जाएंगे तो और electrons भी add होते जाएंगे, right? तो जो inner electrons होते हैं, they provide some kind of a shielding. ये चीज समझ में आई? अभी मैं सिर्फ I'm just explaining it from the top. So अब ये आपको पता है, on going from top to bottom size increases very simply because shells are getting added up, and left to right size decreases because electron gets added up to the same shell. और क्योंकि same shell में add होता है तो न्यूक्लियर चार्ज जब इंक्रीज होता है तो वो आराम से उसको कॉन्ट्रैक्ट कर सकता है. बट इस केस में कॉन्ट्रैक्शन उतनी पॉसिबल क्यों नहीं है? न्यूक्लियर चार्ज तो इधर भी इंक्रीज हो रहा है, बट इस केस में कॉन्ट्रैक्शन इज नॉट रियली दैट मच पॉसिबल, सिंपली बिकॉज ऑफ द रीजन दैट यू हैव सम काइंड ऑफ शील्डिंग इफेक्ट फ्रॉम द इलेक्ट्रॉन्स विच आर गेटिंग एडेड अप बाय द इंक्रीज ऑफ शेल्स. ये थोड़ा थोड़ा समझ में आया? क्योंकि इलेक्ट्रॉन्स उतना इंटरैक्ट नहीं करने देंगे बाहर वालों उसके साथ. सो एज अ रिजल्ट ऑफ विच योर आयनाइजेशन एनर्जी वुड डिक्रीज ऑन गोइंग डाउन द ग्रुप. ऑलराइट, electron affinity would decrease on going down the group. Why? Electron affinity is the energy released when an electron is getting added up. So again, on going down the group, the number of repulsive effects will also increase. And remember, electron affinity ज़्यादा कब होती है? When it is easy to add an electron. Electron affinity is the energy released, and the energy released is more when it is easy to add an electron to the outermost shell. जैसे halogens का configuration क्या होता है? Ns2 Np5. उनकी electron affinity is the highest, right? Now in this case, why is it the highest? Because it is easier to add an electron. So remember, the ease with which you can add an electron to the outermost shell will increase the electron affinity, because the energy released in that case will be more. तो अब क्या होगा? नीचे जाते टाइम it will be more and more difficult to add an electron, so electron affinity also decreases. Again, let's move on to the other concepts. You know that atomic size, we've already talked of size increases. We are just talking about the trend which is for going down the group. ठीक है? अब again the same with the same concept that we have on going down the group, because I'll just put today's class in the form of questions. You try and solve it. Say on going down the group now, what will happen to the hydration energy? Hydration energy is the energy released when what? Solvent interacts with solute. It will decrease. Why? Because on this is what will be the ionic radii in this case. Now the ionic radii will be Be plus, Be2 plus, Mg2 plus, Ca2 plus, Sr2 plus, Ba2 plus and Ra2 plus. We are not talking about this. This is going to be radioactive. Alright, so now on going down the group, we know that the size is increasing. So the smallest ionic size will be possessed by beryllium, which will be the most hydrated, and if it will be the most hydrated, the hydration energy will be the highest in case of beryllium. So the hydration enthalpy, that is why, follows the trend of Be2 plus followed by Mg2 plus followed by Ca2 plus followed by Sr2 plus followed by Ba2 plus. Any doubts for this? Just as same as what we have done for the alkali metals. Alkaline earth metals are also following the same trend. Then we can also talk about remember that these also are forming certain types of hydrates. This information as is given, I'll just put down the formula of some of the hydrates of the chlorides of alkaline earth metals. Like you have MgCl2 and CaCl2. generally exist in the form of hydrates as with 6 water of crystallization, whereas we know that NaCl and KCl do not form such hydrates. NaCl and KCl do not form such hydrates. Can you think of something? I repeat, Mg and Ca2 plus exist in the form of hydrates. Alright, that means there will be some hydration energy which is more in these cases than sodium and potassium. Sodium and potassium chlorides exist as what? NaCl, KCl. Whereas MgCl2 and CaCl2 exist as MgCl2.6H2O and CaCl2.6H2O. One important factor is that on moving from left to right, what happens to the size? It decreases, and when the size is smaller, the tendency of getting hydrated is more. So when it gets hydrated, what happens in that case? The energy for hydration kind of increases, and then you have the tendency of it to have greater number of water molecules to be surrounding it. So remember that alkaline earth metals when compared to alkali earth metals are more hydrated. Okay. Then see, there are some kind of a test. Normally these cations can also be tested. Say supposedly I give you any powdered salt and you do not know what that salt is. So you will have to test it out to find out that as to which cations or which anions are present to find out for the salt. So in that case, one test that can be done is called a flame test. Flame test is you simply add it to some kind of a rod and then put it to the flame, and it will generally impart color. Alright, the color will, that color is characteristic for a particular element. You know why the color is produced? Normally हमारे पास different, अब तो आपको ये पता है different levels होते हैं. I am not going into the details of that. Different levels होते हैं which have electrons filled in them. So normally this electron has a tendency to jump from, जैसे ही heat मिलेगी तो अंदर के subatomic particles हिलेंगे. When the subatomic particles will move, the electron will generally tend to jump from lower level to a higher level, and then it may come back also, right? When it jumps from a lower level to higher level, there is some energy involved, alright, and you know that if that energy which is given by Hc by lambda, if that energy which is given by Hc by lambda, if that wavelength range or the energy range falls in your visible region, क्योंकि visible region का एक wavelength है, wavelength range है 4 into 10 to the power minus 7 to 7 into 10 to the power minus 7. So you have that particular range. अगर इसकी energy उस level में fall करती है, then we will see a color. ये चीज समझ में आई? The color is generally because of the jumping of the electron from one level to another level. Alright. So if we talk about the jumping of the electron from one level to another level, remember that beryllium and magnesium are very tightly bound, alright, such that they do not give any color in the flame. Whereas calcium, strontium and barium, they give characteristic color to the flame. So they can actually give different colors which can help you detect these compounds. But why beryllium and magnesium are not giving? Because their electrons are tightly held. Their sizes are small, electrons are tightly held, and as a result of that, the flame's energy is not sufficient to bring about any jumping of the electron from a lower level to a higher level. So this helps in the estimation of these elements also. Then we can talk about reactivity with air and water. Reactivity with air and water means, see, basically when you are talking about reactivity with air, air में क्या होता है? You generally talk of reactivity with either oxygen or nitrogen, dioxygen or dinitrogen to form oxides or nitrides. Let us tell you in this case that they have a tendency to react, the alkaline earth metals have a tendency to react with oxygen to form oxides. The oxides formed in this case will be, say for beryllium, it will be beryllium oxide, and the nitride which will be formed, what will be the formula of nitride? N3 minus is your nitride. You know this is Be2 plus, so it will be Be3N2. So the oxides and the nitrides formed will have their own formulae. In all the alkaline earth metals, they have a tendency to form the oxides as well as the nitrides. Now with halogens also, let me just tell you here, in this case they also react with water to form the hydroxides. And what will be the hydroxides which will be formed? BeOH twice, because what is OH? OH is minus. So when they react with water, say beryllium, when it reacts with water, it will form BeOH whole twice. So this will be the oxides which will be formed, which will be primarily ionic in nature, because these are also metallic in character, most of them. And remember that the metallic character increases on going down the group, because जब हम नीचे जाते हैं तो size बढ़ रहा है, ionization energy कम हो रही है, तो it is easy to remove an electron from the outermost shells. That is clear? Now because it is easy to remove an electron from the outermost shell, because of that, when we talk about because it is easy to remove an electron from the outermost shell, we can talk about the ionization energy to get decreasing. And here I was talking about the hydration energy, and hydration energy is already talked about. I was talking about the formation of hydroxide. Remember that these hydroxides are primarily ionic in nature, and the ionic character, I am saying that as you move down the group, we know that the ionization energy is decreasing. So the thermal stability or the basic character, what will happen on going down the group? What will happen to the ionic, what will happen? The size is going on increasing. So the basic character is actually expected to go on increasing. I have talked about the metallic character. Ionization energy मैंने इसीलिए बात करी थी because I was trying to explain the metallic character and I got deviated. When we talk about the ionization energy क्या होती है? Energy required to remove an electron from the outermost shell. When we are talking about that, that means अगर it's easy to remove an electron, तो इसका मतलब हमारा 2+ स्टेट जल्दी से अचीव होगा. अगर 2+ स्टेट आराम से अचीव होगा तो हमारा मेटल will be a stronger one, and if it is a stronger one, it will form a good hydroxide also. And as the size increases now, the BeOH bond will get easily cleaved, and because of that the basic character will go on increasing. So basic character increases for hydroxides. Is that thing clear? Another thing that I would like to talk about is that you know the configuration in this case is NS2. Alright. So if I talk about ionization energy to form +2 oxidation state, तो पहले तो ionization energy होगी involved to remove the first electron. Alright. And ionization energy 2 would be to remove the second electron. Now which of them will be more? Ionization energy 1 will be more or ionization energy 2 will be more? Why? In this case, ionization energy 1 means that the energy which is required to form NS1, which is your Be+. Now, you know that it would be willing to give that 1 electron very easily. एक बार इसने ये plus state achieve कर ली, although plus is already a charged species, so to remove an electron, plus मतलब positively charged, और उससे अगर इलेक्ट्रॉन हटाना है तो हमें और ज़्यादा एनर्जी चाहिए क्योंकि पॉजिटिव और नेगेटिव तो आपस में अट्रैक्ट करेंगे. सो आयनाइजेशन एनर्जी 1 इज द एनर्जी रिक्वायर्ड टू रिमूव द फर्स्ट इलेक्ट्रॉन, एंड आयनाइजेशन एनर्जी 2 is the energy required now to remove an electron from Be plus to form it NS0. But you know which is the most stable state? Be2 plus. So it would be very much willing to form Be2 plus from Be plus. So that is why ionization energy 2 in case of alkaline earth metals is much lower than ionization energy 1. Whereas for the case of If I talk about alkali metals now, look up onto the board. If you talk about the ionization energy 1, it will be the energy required to remove the electron from NS1, which means it will become NS0 already. Now, अंदर वाले कौन से होंगे? 2s2, 2p6. Like what is sodium? Sodium is 11. It is 1s2, 2s2, 2p6, 3s1. Up now, what is the ionization energy 1? It will make it 1s2, 2s2, 2p6. ये चीज समझ में आई? 1s2, 2s2, 2p6. तो first ionization energy के बाद अब it is acting as a completely filled like a noble gas. So in that case, now the ionization energy 2 would be very, very, very high in comparison to ionization energy 1. Why? Because it is very, very difficult to remove an electron now from a stable noble gas configuration. Whereas in case of alkaline earth metals, the second ionization energy will be lower. Alright, then after that, here again, when we are talking about beryllium, you can actually check it out that if I talk about the reaction with halogens, what will be the reaction with halogens? What will it form? You tell me. If I talk about reaction with chlorine, it will form BeCl2, MgCl2, CaCl2, SrCl2, BaCl2. Tell me the melting point trend for these chlorides. Can you tell me? I want the melting point trend for BeCl2, MgCl2, CaCl2, SrCl2 and BaCl2. First talk about the covalent character. This can be predicted according to Fajan's rule. For all those of you who know, very good. The ones who have forgotten can just revise it now. Fajan's rule are something that talk about the degree of polarization in ionic compounds. Degree of polarization in ionic compounds. And remember that when we talk about the degree of polarization in ionic compounds, that means we are talking about the degree of covalency that is introduced. This is supported by small size of cation, small size of cation and high charge density, then large size of anions, and high charge density, and electronic configuration if it involves d and f orbitals filling completely in between, like you have argon and all. There if you have the d and the f orbitals already filled up, then those will also have a higher degree of covalency. And greater the degree of covalency, lower will be the melting point. Remember, greater the degree of covalency, lower will be the melting point. अब यहाँ पे जाते टाइम आपका अनायन तो सब जगह पे सेम है, अनायन सेम है, ठीक है. अब cation is getting changed with the same charge, 2 plus 2 plus, तो charge density भी सबकी same है. On going down the group, the size is increasing, so degree of covalency is, अगर size cation का increase हो रहा है, small size होगा तो वो covalent ज़्यादा होगा. तो स्मॉल साइज अगर इसका है तो कोवलेंसी सबसे ज्यादा किस में होगी? BeCl2 में, MgCl2 में नेक्स्ट, फिर इसमें CaCl2 में भी a little more ionic, and then the ionic character is increasing. Why? Because covalent character will now be decreasing down the group. Why would covalent character be decreasing down the group? Because size of the cation is increasing. The charge density is the same, anion is the same, so we do not have to look into that. We will only bother about the size of the cation. So as the size of the cation is increasing down the group, we see that here in this case the covalency would be decreasing down the group, and therefore the melting points would be increasing down the group. Okay, तो ऐसे वैसे ये वाला ऐसा कोई trend दे नहीं रखा होता. It's just your common sense that you have to apply to predict different trends, because you can have infinite number of questions from different compounds. Okay. Then all right, thermal decomposition of how do you actually prepare BeF2? Fluorine is highly electronegative, we know, and small in size also, and Be is also small in size. So preparation of BeF2 can be carried easily by the thermal decomposition of a compound which is NH4 twice BeF4. From NH4 twice BeF4 we can easily form BeF2, alright. And another way of forming BeCl2 is that you can make your oxide react with carbon and chlorine, then it will form BeCl2 and liberate carbon monoxide. Now another important compounds, or another important family of compounds for the alkaline earth metals would be the hydrides. Now when you talk about the hydride formation in this case, what do you think will be formed? You have H as -1 and Be will be +2. So it will be BeH2. BeH2 can be formed by the reaction of BeCl2 with say any reducing agent, good reducing agent like LiAlH4. Lithium aluminium hydride is a good reducing agent. So you can write down the reaction for that. The formation will be, you will have BeCl2 plus LiAlH4, BeCl2, that will give you BeH2 plus LiCl plus AlCl3. Plus Li, what will it give? It will give you BeH2 plus AlCl3 and LiCl. Clear with that? The main thing is you are forming the hydride of beryllium by the action of any reducing agent on beryllium chloride. ये समझ में आ गया? This is how beryllium hydride is getting formed. Now if I ask you to tell me the hybridization for BeH2, I think I told you how to do that. For all those of you who have forgotten, how do we actually carry out the hybridization of beryllium hydride? You first find out the ground state configuration which is NS2. किसी की भी, क्योंकि अगर मैं CaCl2 की hybridization पूछूंगी या CaH2 की hybridization पूछूंगी, उस केस में भी you should know the outermost configuration. Now you are finding out Be in BeH2, what is the hybridization on beryllium. Hybridization is basically centered on one particular atom, so it forms hybrid orbitals centered on that atom. तो इसका oxidation state कितना है? +2. So that means at least 2 electrons should be singly filled. So Ns, or Ns के पास we have, you have talk about Np here. So this is 2s and this is say 2p. So you will have this as the excited state configuration, and you will have an H and an H forming a bond with it. So what will be the hybridization of BeH2? Sp. So what will be the bond angle? 180 degrees. Okay. So this is how your BeH2 would be formed. And talk about reaction of metal with acids. Do you remember as to how we talked about the preparation of dihydrogen? When metal reacts with acids, they form H2. Remember? With alkali also, but here we are just focusing the reaction of metals with acid. So when any of these metals Be reacts with, say, directly with an acid HCl, then what will be formed in this case? You will have BeCl2 and plus H2. So hydrogen gas will be liberated in that case. Okay. And this you already know that the elements have a very high reducing nature. The reducing nature is basically attributed to what? the reducing nature is attributed to very highly negative values of electrode potential. This goes in relation with your redox. जितने भी elements हैं, reducing nature is directly proportional to the very a good negative value of electrode potential. More than the negative value of reduction potential, greater will be the reducing nature. और reducing nature का मतलब क्या है? It will reduce others and oxidize itself. That means it will act as a good reductant. Okay. Now again here the metal in this case again gives a very brilliant color, blue color with ammonia. What is that due to? Last time we had seen that they give blue colored solutions in case of ammonia when used as a solvent. What was that due to? Due to ammoniated electrons. Due to ammoniated. Remember, this is a very important question and asked many a times in your entrance examinations. What is the blue color solution of alkali and alkaline earth metals in ammonia due to? It is mainly due to ammoniated electrons. Ammoniated electrons मतलब जो हमारा electronic species है, that will get solvated by ammonia. How? See, metal जो है वो ammonia के साथ एक तरह का complex बना देगा. It will be NH3 say X times and it will be say plus. अगर M क्या बना रहा है? M plus. तो हमारा साथ में क्या निकलेगा? एक electron and that electron will get associated with your leftover ammonia molecules and will form ammoniated electrons. And in this case you will know that metal will it form a plus state? ये alkali metals में था. Alkali metals में उसने क्या बनाया था? Alkali metals में क्या था? सिर्फ positive, because alkali metals can exist in the +1 oxidation state. Here the most stable oxidation state is +2. So this should be 2 plus. And how many electrons should I have? Twice the number of electrons. So remember that the coloration which is given in case of alkaline earth metals will be more the blue colored. So the coloration will be of a higher intensity in this case. Why? Because the number of electrons which are ammoniated are double in this case. Right? And then you know on standing it can actually give a bronze color also. That is also there. So ammoniates and from this these ammoniates can also be recovered. Then you have very many uses of these compounds also, like hydroxide of magnesium. What is it? What is the hydroxide? MgOH twice. That is also known as the milk of magnesia. That is generally used to cure acidity. So there are other things also, like barium is used in the X-ray diffraction to form the tubes. So you will have many other uses that you can just go through, but by and large remember that the properties are more or less similar to what we have done for the alkali earth metals. Alright, then we have when you talk about the oxides, what will be the oxides which will be formed in this case? What will be the oxides formed? MgO, BeO, CaO, SRO. Why? Because O is 2 minus and B is 2 plus. So I am not writing those reactions at all, you know. ठीक है, चलो अब ऊपर से नीचे जाते टाइम मेटालिक कैरेक्टर का क्या होता है? मेटालिक कैरेक्टर सोच समझ के बोलना. It takes only a second to think. Alright, metallic character increases. तो हमारे जो मेटालिक वाले ऑक्साइड्स होते हैं, they are generally known to form with water. What do they form? Acid or base? Base. So the ones which are actually metallic in nature will be forming basic oxides, and the ones which are a little non-metallic or which have less metallic character are known to form acidic oxide. But ये सारे तो हम क्या बोलते हैं, ये सब क्या है? Metals. It is only that the metallic character is increasing down the group. So बाकी सब तो बेसिक ऑक्साइड्स फॉर्म करते हैं. Be जो है वो एम्फोटेरिक ऑक्साइड फॉर्म करता है. ठीक है, एम्फोटेरिक ऑक्साइड इज द वन व्हिच कैन रिएक्ट बोथ विद एसिड as well as a base, whereas the basic oxides are the ones which essentially form a base on reacting with water and also have the property of reacting only with base. Okay, so See, they generally form this solubility of, all right, let me just talk about BeO, then you have MgO, CaO, SRO, etc. And the hydroxides which will be formed will be BeOH twice, alright, then you have MgOH twice, let me just put it like that, and you have CaOH twice, and you have SROH, let me just talk about these, alright. Ab, melting point trend for these. Do you want me to put 4 options or you will tell me the correct answer? Melting point trend for BeO, MgO, CaO, SRO. मेल्टिंग पॉइंट ट्रेंड किससे आप बताओगे? कोवेलेंट कैरेक्टर देख के, ठीक है। ऊपर से नीचे जब हम जा रहे हैं तो कटायन का साइज बढ़ रहा है, अगर कटायन का साइज बढ़ रहा है तो कोवेलेंट कैरेक्टर कम हो रहा है, तो हमारा मेल्टिंग पॉइंट इंक्रीज होगा। वेरी गुड, ऑलराइट, तो मेल्टिंग पॉइंट विल इंक्रीज। ऑलराइट, लेट्स टॉक अबाउट दीज। हमने अभी हाइड्रोक्साइड्स के बेसिक कैरेक्टर की मैंने बात करी थी, होप यू रिमेंबर दैट। जब हम ऊपर से नीचे जाते हैं तो बेसिक कैरेक्टर मैंने बोला था विल इंक्रीज। वेरी गुड, बेसिक कैरेक्टर इंक्रीज क्यों होगा? क्योंकि मेटल का साइज बढ़ रहा है, तो वो MOH, आपको पता है अकॉर्डिंग टू आर्हेनियस कॉन्सेप्ट, व्हेन विल दिस एक्ट एज अ बेस? द वन व्हिच गिव्स OH माइनस आयंस इज अ बेस, द वन दैट गिव्स H प्लस आयंस इज अ एसिड। तो ये तो एसेंशियली बेस की तरह एक्ट करेगा। अब वो बेस तभी बेस होगा ना जब ये OH आराम से क्लीव करेगा। Be is attached to OH and OH, alright. B is attached to OH and OH. जब ये बॉन्ड आराम से टूटेगा तभी तो हम कहेंगे कि it's a stronger base. And because when we move from top to bottom, the size goes on increasing and the stability goes on decreasing. So we say that the basic character goes on. ठीक है, तो इसका मतलब वो आराम से टूटेगा। अब मुझे बताओ, what will be the trend for solubility for hydroxides? सोच के think of a reason. You know the reason. What will happen to the solubility trend for these hydroxides? Increases down the group. Why will it increase down the group? Because अगर OH minus आराम से ions बना रहा है, basic मतलब क्या? It will form what? It will form Ca2 plus and OH minus ions, Mg2 plus and OH minus ions. और जितने आराम से ये ions बनाएगा उतनी जल्दी ये soluble होगा। Greater the polarity, more will be the ease with which it can actually become soluble. Any doubts about that? Alright, let's talk about the structure now of the halides. ये मतलब आप ही ने बताया, मैंने इसमें कुछ खास नहीं पढ़ा है। You know the reason and now you can apply these reasons to other things as well. ठीक है, अब एक चीज यहाँ पे ही बता देती हूँ। ये तो हाइड्रोक्साइड्स था तो इजी था। मान लो हाइड्रोक्साइड नहीं है, कार्बोनेट है, सल्फेट है, ये वाली सॉल्ट्स भी तो बात करेंगे ना। कार्बोनेट बनाएगा तो क्या बनेगा फॉर्मूला? BeCO3। सल्फेट बनाएगा तो क्या बनेगा? MgSO4। ठीक है, सल्फेट बनेगा तो ये फॉर्मूला बनेगा। अब जब इनकी सॉल्युबिलिटी की बात करेंगे तो यू हैव टू टेक केयर ऑफ 2 इम्पोर्टेंट फैक्टर्स। बी वेरी केयरफुल बिकॉज क्वेश्चंस रीजनिंग के ही आते हैं इसमें से, और ट्रेंड्स। इसके अलावा जो रिएक्शंस आर वेरी सिंपल। इफ यू जॉट देम डाउन, हार्डली आई थिंक 10 और मोर, राइट? सो इफ आई एम टॉकिंग अबाउट solubility in any solvent or especially water, there are 2 factors which are important. Remember those: lattice energy and hydration energy. Will you remember what are the 2 factors? Lattice energy and hydration energy. पहले मैं यही समझा देती हूँ, then I'll talk about any other salt. ये तो फजान्स रूल के अकॉर्डिंग, ये वाला मैंने मेल्टिंग पॉइंट ट्रेंड पूछा था। ये बेसिक कैरेक्टर वेंट अकॉर्डिंग टू द साइज ऑफ द आयन एंड द वे बॉन्ड डिसोसिएशन एनर्जी। क्योंकि साइज बढ़ गया, बॉन्ड डिसोसिएशन एनर्जी कम हो गई, OH माइनस आराम से देगा तो बेसिक ज़्यादा हो गया। और बेसिक से हमने फिर वी टॉक्ड अबाउट सॉल्युबिलिटी ऑल्सो, जो जितनी आराम से टूटेगा उतनी जल्दी वो आयंस बनाएगा, एंड इफ इट फॉर्म्स आयंस इजीली इट इज मोर soluble. So these trends are absolutely clear to you. Now I was talking about other things now. If I am talking about the solubility of the salts of the alkaline earth metals in water, there are two factors which are important. Attention onto the board, because these are those concepts that you will be using throughout in organic chemistry, even in 12th. One is the lattice energy and the other is the hydration energy. ठीक है, lattice energy को कई बुक्स में आप देखोगे it's written as U naught, alright, and hydration energy is your simply ऐसे लिखा होता है delta H hydration. That's the way of writing it. So just remember these things, that when I am talking about lattice energy, what is lattice energy? It is the energy released when two ions from infinite distance apart are brought together to form a bond. I repeat, lattice energy क्या होती है? It is the energy released to form an ionic solid. ये चीज समझ में आई? It is the energy released to form an ionic compound. Energy released to form an ionic compound. अब ionic compound बनेगा किससे? Ion से. ठीक है, अब वो ions आएंगे कहाँ से? When we have two, it is what, जब दो आयंस m प्लस और x माइनस कोई भी, उनको जब हम इनफाइनाइट डिस्टेंस से पार्ट से पास लाके उनका आयनिक कंपाउंड बनवा रहे हैं, मतलब बॉन्ड बनवा रहे हैं, उनका जब बॉन्ड बनवाएंगे तो द एनर्जी विच इज रिलीज्ड एट दैट टाइम, दैट एनर्जी इज नोन एज लैटिस एनर्जी. आई रिपीट द डेफिनेशन, इट इज द एनर्जी रिलीज्ड when two oppositely charged ions are brought from infinite distance apart to a particular distance considered to form an ionic compound. ये चीज समझ में आई? अब ions don't exist as such in gaseous form. Ions तो as such है नहीं यहाँ पे, वरना एकदम से अगर current कहीं produce होगा तो एकदम से it will be like a bomb, because you, if ions are there, they can easily transfer the charge. They're capable of transferring many of them. So here lattice energy की चीज मतलब समझ में आया कि if I am talking about m plus x minus to form m plus x minus, then I am m plus x minus ionic compound, then the energy released is your lattice energy. And hydration energy is the energy released when you are talking about the solvation or the interaction of solute with water. I have already told you that when we talk about the solubility factor, the solute solvent interaction should be more than solute solute and solvent solvent interactions. We've already talked about it. So the energy released when a solute solvent bond should be sufficiently more to break the solute solute bond and the solvent solvent bond. कुछ समझ में आया? अब शॉर्टकट बताती हूँ, मतलब समझ में आया या नहीं आया? Remember this particular fact that if I say a particular salt, this is a shortcut, a particular salt is soluble in water, और वो soluble क्यों है? तो इसका मतलब hydration energy is greater than lattice energy. और अगर वो insoluble है तो insoluble क्यों है? Because lattice energy is greater than hydration energy. क्योंकि अगर lattice energy ज़्यादा है तो इसका मतलब वो इसी फॉर्म में रहना पसंद करेगा, बॉन्डेड फॉर्म में, और अगर हमारी हाइड्रेशन एनर्जी ज़्यादा है तो वो वाटर के साथ इंटरैक्ट करके उसको ब्रेक करने में ज़्यादा उसका इंटरेस्ट रहेगा. ये चीज़ समझ में आई? तो अगर कोई भी क्वेश्चन आता है, दिस सल्फेट द ट्रेंड ऑफ सॉल्युबिलिटी इंक्रीजेज और डिक्रीजेज, तो अकॉर्डिंगली यू नो हाउ टू आंसर द क्वेश्चन. दिस इज जनरली आस्क्ड इन रीजनिंग क्वेश्चंस. नाउ लैटिस एनर्जी के लिए एक जो कॉन्सेप्ट आपके बेसिक चैप्टर्स में है, आई एम जस्ट रिवाइजिंग इट फॉर यू. लैटिस एनर्जी कैन नॉट बी एक्सपेरिमेंटली डिटर्मिन्ड, बिकॉज लैटिस एनर्जी आयंस को साथ में लाकर निकालने वाला एक चीज़ है, तो इट कैन नॉट बी वेरी इजीली एक्सपेरिमेंटली डिटर्मिन्ड. तो उसको निकालने के 3 तरीके होते हैं. यू एक्चुअली हैव एन इक्वेशन कॉल्ड द बॉर्न-लैंडे इक्वेशन, देन यू हैव कैपुस्टिन्स्की इक्वेशन. घबराना नहीं, ये करने नहीं है. कैपेंस्टन्स की इक्वेशन एंड यू हैव अ बॉन्ड हेबर साइकिल ही करना है, ठीक है। कई मेथड्स हैं, इनसे क्या करते हैं हम, वी कैन फाइंड आउट आवर लैटिस एनर्जी. बॉन्ड हेबर साइकिल इज important. That's there in your course, asked in the JEE exam also. Alright, so how do you actually take care of that bond Haber cycle? देखो, thermodynamics पढ़ा है? मत सुनो. What is the main one which is important? It is the bond Haber cycle. And lattice energy हम क्यों निकालते हैं? Because it is very difficult to determine it experimentally. तो उसके लिए हमें कोई थियोरेटिकल वे फाइंड आउट करना होता है. अब थर्मोडायनेमिक्स पढ़ा है, ठीक है. व्हाट इज द एनर्जी एंथैल्पी कॉल्ड फॉर फॉर्मिंग 1 मोल ऑफ अ सॉलिड? इट इज द हीट ऑफ फॉर्मेशन और एंथैल्पी ऑफ फॉर्मेशन. जब 1 मोल ऑफ सॉलिड बनाते हैं तो हमारा इजी तरीका क्या है, हम m प्लस x2 बनाएं, जैसे सोडियम बेरिलियम कुछ भी. चलो पहले सोडियम ले लेती हूँ, सोडियम प्लस एग्जाम्पल ले लेती हूँ Cl2. जब हम ये बना रहे हैं तो हमारा क्या बनेगा आपको पता है? What will get formed? Tell me quickly. It will form NaCl. ठीक है, it will form NaCl. Now this is what we want, the formation of NaCl. पर ये हमारा नॉर्मल सोडियम क्या है? सॉलिड. क्योंकि अगर आपको NaCl बनाना है तो आप क्या करोगे? सॉलिड उठाओगे, क्लोरीन गैस लोगे and you will make the two react to form NaCl. So now, and chlorine is what? Chlorine is a gas. And ये अब enthalpy इसको मैं क्या कहूँगी? The enthalpy of, this is the enthalpy of formation. ठीक है, ऊपर देखो, कुछ लिखने की ज़रूरत नहीं है, क्योंकि for JEE you just have to remember the final expression and the final formula. So this is the enthalpy of formation. जब हम Na को अब मैं convert कर रही हूँ टू, अब मुझे बनाना क्या था ये, अगर NaCl मुझे सॉलिड आयनिक सॉलिड बनाना है, लैटिस एनर्जी कैसे पता चलेगी? व्हेन आई विल गेट दिस कंपाउंड गेटिंग फॉर्म फ्रॉम Cl माइनस एंड Na प्लस. ठीक है, तो इसका मतलब मुझे Na प्लस और Cl माइनस चाहिए एंड द एनर्जी रिलीज्ड विल देन बी योर लैटिस एनर्जी. क्लियर? ऊपर देखो, लिखो नहीं. So this will be lattice energy. Now what will happen? Ions generally exist in the aqueous or gaseous state. I mean you can actually create them. अगर हम इसको क्योंकि gas can easily get dissolved in water. Ions are some ionic state. You know that there is an ionosphere also which is existing. There you do not have high water. There the ions are not ion. You know that there are in your atmosphere you have different layers: troposphere, mesosphere, ionosphere, stratosphere, and so on. So there you are talking about ions. So ions to be existing in the gaseous form, now you will be bringing them together to form NaCl. That's called lattice energy. अब ये reaction करना तो possible नहीं है ना? तो अब हम क्या करेंगे? सबसे पहले Na से हम solid को sublime करेंगे तो Na gas बनेगी. What will this be called? Sublimation energy. आप इसको लिखते हैं ऐसे हो, delta H sublimation. मैं सिर्फ S लिख रही हूँ so that you remember. This is called sublimation energy. अच्छा, अब ये बताओ इस एनर्जी को मैं क्या कहूँगी? Na forming Na plus. Ionization energy. Very good. This is ionization energy. All right. Now Cl2 को मुझे तोड़ के Cl निकालना है पहले, तो I'll form what? Cl. तो इसमें कौन सी एनर्जी इन्वॉल्व होगी? डिसोसिएशन एनर्जी, क्योंकि डिसोसिएट करना है तो दिस विल बी डिसोसिएशन एनर्जी. अब इस Cl से मुझे बनाना है Cl माइनस. सो व्हाट विल दिस बी? इलेक्ट्रॉन एफिनिटी. हर बार आयनाइजेशन थोड़ी, क्योंकि Cl में इलेक्ट्रॉन इज गेटिंग एडेड अप. सो दिस विल बी इलेक्ट्रॉन affinity and this is your lattice energy. Alright, so according to Hess's law of constant heat summation, the energy which is involved in one step can be equal to the energy enthalpy involved in several steps. तो ये एक स्टेप की रिएक्शन है, ठीक है, क्योंकि मेन रिएक्शन तो ये थी डेल्टा HF. तो इसका मतलब जो मेरा डेल्टा HF है, हीट ऑफ फॉर्मेशन ऑफ द आयनिक सॉलिड, that is equal to this enthalpy plus this enthalpy plus this plus this plus this. ठीक है, क्योंकि इन सबको ऐड करके ही तो हमारा NaCl बन रहा है. Got the point? So that means according to Born-Haber cycle, what is the heat of formation equal to? Repeat it after me. It is S D I E U, where E is the energy released and U is the energy released. इसको मैं प्लस प्लस इसीलिए लिखवाती हूँ क्योंकि जब डेटा गिवन होता है तो वो नेगेटिव नेगेटिव गिवन होता है. बुक्स में ना आपको ये ऐसे दिया होगा क्योंकि ये एनर्जी रिलीज्ड है, पर अगर आपको फिर डेटा माइनस में गिवन है ना तो आप इसको पॉजिटिव कर देते हो, विच इज नॉट करेक्ट, क्योंकि दैट नेगेटिव इज टू बी टेकन लाइक दैट. इट इज द एनर्जी रिलीज, और आपको पता है एनर्जी रिलीज्ड इज शोन एज नेगेटिव वैल्यू, राइट. सो नाउ रिमेंबर व्हाट इज दिस डेल्टा एच एफ, दैट्स इक्वल टू एस डी आई ई यू. रिपीट इट, व्हाट इज डेल्टा एच एफ? louder. All right, S for sublimation, D for dissociation, I for ionization, E for electron affinity, U is your lattice energy. अब lattice energy का मतलब clear है? तो lattice energy is that energy which is released when an ionic compound is formed from ions. और जितनी ज़्यादा वो होगी उतना मुश्किल है हमारे उस बॉन्ड को तोड़ना, और फिर उतना ही मुश्किल है उसके लिए डिसॉल्व होना. ओके, I could have taken more examples from this, but because of paucity of time I will not be able to do this. This is also a part of your thermochemistry. Okay, so now let me just give you some questions. First of all, सबसे पहले बेरिलियम क्लोराइड का स्ट्रक्चर जो होता है ना, see it is BeCl2. BeCl2 बनता है, just look up, we form BeCl2 and even for Be we, so normally क्या होता है, बेरिलियम is 1s2 2s2, alright, and it doesn't fall under the category of the octet rule. It's an exceptional case because these are known to be electron deficient compounds. So first of all, it exists generally in a chain like structure where it extends its covalency to form a chain like structure like this. Alright, remember that BeCl2 exists in a chain like structure which is something like this. So it can extend its covalency, that's one point, and it exists as a linear monomer only in case at 1200 Kelvin. At 1200 Kelvin it exists only as a linear monomer. मोनोमर का मतलब जिसमें सिर्फ एक ही मॉलिक्यूल है, डाइमर का मतलब जिसमें दो मॉलिक्यूल्स इन्वॉल्व्ड हैं, ट्राइमर मीन्स 3 and polymer is in which many are involved. So now here in this case BeCl2 exists as a chloro-bridged dimer generally. Generally it exists as a dimer only. Now the question is, BeF2 is very less soluble than BeCl2. Why? और एक चीज़ याद रखना, जब हमारा कटायन और अनायन दोनों ही छोटे छोटे होते हैं तो लैटिस एनर्जी बहुत ज़्यादा हाई होती है, ठीक है. जितने ज़्यादा छोटे छोटे आयन्स होंगे उतनी ज़्यादा एनर्जी रिलीज होगी. When two kids interact or when you two interact, I mean two from your batch interact, who release more energy? Kids. So you can remember it that way. Weird example, but then you can just talk about this now. Yeah. मैंने बोला है मैंने नहीं, बुक में लिखा है BeF2 is less soluble than BeCl2. Tell me the reason. Come straight to the answer. Lattice energy is very very high. So you gave me the answer saying that the lattice energy in this case is going to be very very high. Alright, form the carbonates of alkaline earth metals quickly. ठीक है, अब carbonates of alkali metals are more soluble. ध्यान से सोच के रीजन बोलना. Carbonates of alkali metals are more soluble, but carbonates of alkaline earth metals are a little less soluble in water. Why? यहाँ पे आप कटायंस, क्योंकि अनायन सेम है तो कटायन के साइज को भी कंपेयर कर सकते हो, कटायन के साइज को कंपेयर करते हैं. तो अगर कटायन का साइज क्या हो रहा है, कम हो रहा है, तो कोवेलेंट कैरेक्टर, फजान्स रूल. पहले मुझे फजान्स रूल बताओ, कोवेलेंट कैरेक्टर ज्यादा कब होगा? When will the covalent character be more? When the size of the cation is small. When the size of the anion is high, large. Okay, when the size of the anion is large, along with high charge density. Alright, along with high charge density. तो अगर हम लेफ्ट टू राइट जा रहे हैं तो एल्कली से एल्कलाइन अर्थ मेटल में साइज क्या हो रहा है? डिक्रीज. तो कोवेलेंट कैरेक्टर क्या हो रहा है? इंक्रीज. अगर कोवेलेंट कैरेक्टर इंक्रीज हो रहा है कार्बोनेट्स का, तो इसका मतलब पानी में सॉल्युबिलिटी के लिए वो कम पोलर होंगे. आयनिक तो दोनों ही हैं, BeCO3 और सॉरी द एल्कलाइन अर्थ मेटल कार्बोनेट्स एंड योर Na2CO3 एंड एटसेट्रा, दोज आर आल्सो आयनिक. लेकिन कोवेलेंसी किस में ज़्यादा है? एल्कलाइन अर्थ मेटल्स में. तो उसकी वजह से सॉल्युबिलिटी किसकी ज़्यादा होगी? एल्कली अर्थ मेटल, एल्कली मेटल्स की. फर्स्ट ग्रुप. ऑलराइट, एंड द सेकंड ग्रुप विल हैव lesser solubility. Alright, so you'll have different questions based on that. Alright, let me just give you more questions based on it. Alright, here talk about carbonates, talk about the stability of carbonates now. You have BeCO3, MgCO3, CaCO3, alright, SrCO3. फर्स्ट ऑफ ऑल जो चीज़ें नहीं गिवन मैं वो पूछती हूँ, फिर आप ये वाला आंसर दे पाओगे. मैंने थर्मल स्टेबिलिटी पूछ रही है, तो confusion, questions, running, I can see so many question marks in the air. So here what we have is BeCO3, magnesium carbonate, calcium carbonate, strontium carbonate. दो तीन rules अब पता हैं, जैसे वो lattice energy, hydration energy का फंडा, and you know about Fajan's rule. Now here if I talk about carbonate, सबसे पहले तो ये आता है anion same है, let's compare the size of the cation and Fajan's rule apply करके देखते हैं. ठीक है, अगर Fajan's rule apply करके देखेंगे तो which will be the most covalent? Tell me. Which is the most covalent? It is the most covalent. All right. So covalency इसका मतलब नीचे जाते टाइम decrease हो रही है. Covalency is decreasing. If covalency is decreasing, that means melting point is. If covalency is decreasing, that means melting point is increasing. क्योंकि मैंने बोला covalent character ज़्यादा होगा तो melting point कम होगा. अगर मेल्टिंग पॉइंट इज इंक्रीजिंग मतलब मुझे ज्यादा टेम्परेचर प्रोवाइड करना है टू ब्रेक द बॉन्ड. तो अब बताओ फिर थर्मल स्टेबिलिटी. थर्मल स्टेबिलिटी अब दोबारा कोवेलेंसी सबसे ज्यादा किस में है? क्यों? स्मॉल साइज ऑफ cation. All right, so this is the most covalent. So on going down the group, the covalency of these carbonates is decreasing. So melting point is increasing, and if melting point is increasing, मतलब मुझे ज़्यादा temperature देना है to break the bond. So that means वो ज़्यादा stable होगा. So thermal stability is increasing, is more on going down the group. कोई शक? Alright, so is that clear? Thermal stability increases with increasing cationic size. अब correct कर लो. Thermal stability may be in a flow sometimes, you know, increase, decrease करते करते slip of tongue may happen, which should not happen. I apologize if I said something like that in one of the lectures. Please take a note. अब तो clearly step wise समझाया ना. टाइम इतना होता नहीं है. तो remember that small size of the cation means more covalency means less melting point means unstable, greater instability. Do you want me to repeat that? So please correct it in the last class if at all I said that the thermal stability decreases down. The thermal stability is in fact increasing down the group for carbonates of alkaline earth metals. Okay, for carbonates of alkaline earth metals. All right, let's talk about sulfates. All right, form the sulfates now quickly. BeSO4. अच्छा मैं एक बात बता रही हूँ, सल्फेट का साइज थोड़ा बड़ा होता है और ये वाले जो कटाइंस हैं they generally tend to form ionic compounds with sulfates. So sulfates are somewhat more ionic in nature otherwise in comparison to the carbonates and others. So BeSO4, now MgSO4, CaSO4, then you have calcium, strontium, barium. These will be the sulfates which will be formed, alright. Now I am telling you now, just listen, beryllium sulfate and magnesium sulfate are readily soluble in water. ठीक है, क्या बोला मैंने? Beryllium sulfate, magnesium sulfate are readily soluble in water, whereas solubility decreases from calcium, strontium to barium. So solubility is going on decreasing. Reason, अगर they are soluble in water means what is more and what is less, because अगर कोवेलेंसी चेक करोगे यहाँ पे तो गड़बड़ हो जाएगी, बिकॉज कोवेलेंसी हमेशा स्मॉल कटाइन की ज़्यादा होगी. अगर ये ज़्यादा कोवेलेंट होता तो ये पानी में उतनी इजीली डिसॉल्व नहीं होता. दैट मीन्स दीज आर आयनिक इन नेचर. एक चीज़ तो यहाँ से प्रूव हो गई. अब ये तो मिलाकर ही देखेंगे तभी ये एक्सपेरिमेंटल फाइंडिंग है, लेकिन अब रीज़न आपको देना है कि वाई आर दीज टू रेडिली सॉल्युबल इन वाटर. आई हैव जस्ट टॉट यू because hydration energy is much greater than. ये बनेगा कैसे? आयनिक अगर है तो कैसे बनेगा? Be2 प्लस और SO4 2 से, तो इसके अंदर लैटिस एनर्जी इन्वॉल्व होगी. और अगर हाइड्रेशन एनर्जी हमारी लैटिस एनर्जी से ज़्यादा है तो इट विल बी सफिशिएंट टू ओवरकम द Be2 प्लस एंड SO4 2 का बॉन्ड. समझ में आया? तो इफ दीज टू आर रेडिली सॉल्युबल इन वाटर, द रीजन इज व्हाट, दैट द हाइड्रेशन एनर्जी इज मच ग्रेटर देन lattice energy. All right, next we can talk about nitrates. और इतना भी याद रखना, आपको ये भी पता है कि जो आयन जितना छोटा होता है उसकी हाइड्रेशन एंथैल्पी उतनी ज़्यादा होती है. तो ये वाला रीज़न भी जनरली फॉर मेनी सॉल्ट्स इट्स एप्लीकेबल दैट द स्मॉलर साइज्ड आयनिक सॉल्ट्स are generally more soluble because the hydration energy is much greater than lattice energy. Okay, then we talk about nitrates. Nitrates are generally formed by dissolution of carbonates in nitric acid. तो हमारे जो nitrates होते हैं ना, they generally decompose on heating. Decompose का मतलब the moment you going to heat them, they will form oxide plus nitrogen dioxide and oxygen. They decompose on heating, that means they lose their identity as a compound and form the metal oxide along with nitrogen dioxide and oxygen. And they also show a decreasing trend, a tendency to form hydrates. जो nitrates हैं, they are less hydrated or with increasing size, and hydration enthalpy decreases down the group. Hydration enthalpy decreases down the group. अगर hydration enthalpy decreases down the group मतलब नीचे वाले जो हैं वो soluble in water नहीं होंगे. Now let me just give you a question and you try and solve it. Why does the solubility of alkaline earth metal oxides in water, hydroxides की solubility in water increases down the group? मैंने reason कुछ और दिया था, मैंने आपको basicity से link करके दिया था, पर अगर तरीके से if you have to use the correct terms, so why will the solubility of alkaline earth metal hydroxides मतलब BeOH twice, MgOH twice, इन सब की hydroxides की solubility in water decreases down the group? क्यों? इन सब की let me tell you, lattice energy remains almost the same. Here in this case, no, the lattice energy भी ऊपर से नीचे जाते टाइम decrease होगी, क्योंकि लैटिस एनर्जी सबसे ज़्यादा किसकी होगी? जिसका छोटा सा साइज होगा, तो लैटिस एनर्जी भी कम हो रही है. हाइड्रेशन एनर्जी भी नीचे जाते टाइम कम हो रही है, क्योंकि हाइड्रेशन एनर्जी सबसे ज़्यादा किसकी होगी? जो सबसे छोटा होगा सबसे ज़्यादा हाइड्रेशन एनर्जी भी उसकी होगी, जो सबसे छोटा होगा लैटिस एनर्जी भी उसी की ज़्यादा होगी. अब जब हाइड्रोक्साइड बन रहे हैं एंड वी आर सेइंग दैट द सॉल्युबिलिटी ऑफ हाइड्रोक्साइड इज इंक्रीजिंग डाउन द ग्रुप, तो पहले मैंने रीज़न ये दिया था क्योंकि वो बेसिक ज़्यादा होते हैं तो नीचे वाले आराम से डिसोसिएट होंगे तो आराम से डिसॉल्व हो जाएंगे. But in terms of lattice and hydration energy, how do you count for it? That the hydration energy also decreases, but lattice energy decreases more rapidly, such that the hydration energy will be greater than the lattice energy, and that difference goes on increasing down the group. समझ में आया? अगर solubility ज़्यादा है तो किसकी वजह से है? हाइड्रेशन एनर्जी. और अगर इंसॉल्युबिलिटी ज़्यादा है तो वो किसकी वजह से? लैटिस एनर्जी. तो ऊपर से नीचे जाते टाइम दोनों लैटिस एनर्जी और हाइड्रेशन एनर्जी डिक्रीज हो रहे हैं, पर द डिक्रीज इन लैटिस एनर्जी इज मच फास्टर और मच मोर सिग्निफिकेंट. फास्टर नहीं, मच मोर सिग्निफिकेंट in comparison to hydration energy. And because hydration energy now is more than lattice energy, they are soluble and solubility increases on going down the group. You should be able to predict the trend. Alright, then talk about the solubility of carbonates. Solubility of carbonates, if I talk about कौन से carbonates हैं, you have BeCO3, MgCO3, SrCO3. अभी हमने थर्मल स्टेबिलिटी की बात करी थी, सॉल्युबिलिटी की नहीं करी थी. तो अगर मैं कह रही हूँ द सॉल्युबिलिटी इज डिक्रीजिंग डाउन द ग्रुप. नाउ पहले तो थर्मल स्टेबिलिटी इज इंक्रीजिंग डाउन द ग्रुप, वो टूटेगा ही नहीं, तो सॉल्युबल होने का तो वैसे सवाल ही नहीं है. पर सॉल्युबिलिटी इफ इट हैज टू बी एक्सप्लेन्ड इन टर्म्स ऑफ टू टर्म्स, lattice energy is now in these cases becoming more and more prominent over hydration energy. So you will say that देखो lattice energy और hydration energy दोनों decrease होंगे with change in size, you know that. छोटे वाले size का ज़्यादा होगा दोनों, लेकिन दोनों if they are decreasing तो किसका decrease कितना ज़्यादा होगा? So that value has to decide. So as we move down the group, the lattice energy is going to be more and more prominent over the hydration energy. और अगर वो ज़्यादा होगी तो solubility will be less. So solubility decreases down the group. फिर बोल रही हूँ अगर solubility कम हो रही है तो वो lattice energy की वजह से हो रही है, और अगर solubility बढ़ रही है तो वो hydration energy की वजह से बढ़ रही है. ठीक है? Okay, then we talk about the anomalous behavior of beryllium. You know that beryllium के अंदर because it's the topmost element, it has a small size, high ionization energy, high electron affinity, it can get easily hydrolyzed, it can form largely covalent compounds. ये सब चीज़ें तो I think now you can just tell by just missing out one or two which you shouldn't. Alright, उसके अलावा beryllium does not exhibit coordination number more than 4. Beryllium वो small size वगैरह वाली तो सारे points हैं, small size, high electron affinity, high ionization energy, then what else did I say, more covalency. Why more covalency? Because the cationic size is the smallest in this case, and so if there is more covalency the melting point should be the least in its compound generally. ठीक है? So thermal stability should also be the least. तो ये सारे points तो are from the basic characteristic. We are talking about beryllium. Alright, then the next thing is that we can also talk about beryllium. It does not exist its coordination number greater than 4. This is not possible. Beryllium cannot extend its coordination number to greater than 4. तभी it exists as a dimer. जैसे BeCl2 वगैरह है, it exists as a dimer. Another thing is that when you talk about the coordination compound, remember that the remaining can actually, the rest can extend. Why can they extend? You have to give me the reason. The rest, they cannot extend their coordination number to greater than 4. But why can the rest extend? ऐसा क्या है बाकी सबके पास? They have vacant d orbitals also apart from the vacancy, and the size is also sufficient to accommodate them. Then the oxide and hydroxide of beryllium, what was the special feature about oxides and hydroxides? You tell me. बाकी सब तो basic थे, ये दोनों क्या थे? Amphoteric. So they were amphoteric in nature. So 3 anomalous behavior हमने cover कर लिए. एक उसकी size की वजह से बहुत सारी problems हैं. Problems नहीं है, वो different है. Sorry. So वो different कैसे है? Small size, high ionization energy, high electron affinity, more polarization because of small size, and lower melting point because the covalency is high. ठीक है, ये सब points. उसका covalent it cannot extend its coordination number to greater than 4 because उसके पास extra orbitals भी available नहीं है, and then the size is also not permitting that, but the rest can actually extend. Whereas another thing is that the beryllium oxide and hydroxides are generally amphoteric in nature, whereas all the rest are dash in nature. All the rest are basic. Alright, then you tell me what will beryllium show its diagonal relationship to? Beryllium shows its diagonal relationship to what? Beryllium किसके साथ diagonal relationship show करेगा? You have beryllium, बेटा मांगे कार और स्कूटर, पापा राजी, right? You have B माँ का strontium 12. So you have beryllium, magnesium, calcium, strontium, barium, calcium. And then next, अब जो P block होगा इसके बाद सीधा जिसकी हम बात करेंगे. So P में what do we have? B. Then you have boron family, and boron family is what? It is बैंगन, आलू, गाजर in थैली, थैला, थैली, whatever. So you have right? So what will beryllium show its diagonal relationship to? With aluminium, alright? It will show its diagonal relationship to aluminium. That's like an anomalous behavior of the first topmost element of each group, that it is similar to, it shows many properties which are similar to the second group of the next, second element of the next group. Okay? So here the those properties are what? I'll just summarize those properties. Like aluminium, beryllium is not attacked by acids. It is not attacked by acids. Why is it not attacked by acids? This is a reasoning question. Because beryllium जो है ना, वो oxygen के साथ it reacts with air and forms an oxide film on top of it. तो वो oxide film acts as a protective layer, and so it is not readily attacked by acids. It is because of the formation of the oxide film. Then both beryllium and aluminium form berylate ions and aluminate ions. Alright, it forms berylate ions and it forms aluminate ions. ये brackets का क्या significance है? Square brackets है? What is the significance of these brackets? कि the charge. So this is acting as a coordination sphere. मैंने क्या difference बताया था? Coordination compounds की properties ये होती हैं कि even if you put them in water, they will remain intact. मतलब जैसा ये square bracket के अंदर है, ये वैसा ही रहेगा, लेकिन बाकी के salts जो हैं वो totally dissociate हो जाते हैं. But so that means beryllium and aluminium are actually extending to form what? Berylate ions and aluminate ions. So they can form this. Alright, the next thing is that chlorides of both beryllium, BeCl2 and AlCl3, they exist in the form of bridges. They form bridged chloride structures and generally in vapor phase. They form bridged structures in vapor phase, alright. And also that they have a strong tendency to form complexes like they have a strong tendency to form complexes. Complexes होते हैं, you know that all these are complexes. Complex पता है, complex वो which are the coordination compounds. Your coordination compounds are by and large what? They are the complexes only. अच्छा, यहाँ पे they are forming bridge bonds, all right. पर एक चीज देखो, अभी भी इनके पास electrons तो कमी है, octet तो तब भी नहीं complete होगा. Be is 2,2, जैसे वो KLMN shells में नहीं बोलते थे. Be is 4, so 2,2. तो it is taking only one electron from chlorine. क्योंकि bond is formed by 2 electrons, एक electron beryllium का, एक electron chlorine का. So it only has say 4 electrons involved in the bond formations. 4 इलेक्ट्रॉन्स, अभी भी 4 कम है, तो उसके लिए वो ब्रिज स्ट्रक्चर फॉर्म करता है। एक चीज तो ये, तभी ब्रिज ऐसे बनता है ना, जैसे what is it, beryllium is what, it will be 2,2, it will be 2,2, so 2 ये है तो it has taken 2 more electrons, तो ये क्या हो गया 4। अब बाकी तो है नहीं, तो it what it does is it combines with the other, so basically यहाँ पे है तो 3 सेंटर, लेकिन इलेक्ट्रॉन्स कितने हैं, सिर्फ 2 इन्वॉल्व्ड, क्योंकि ये तो एक्स्ट्रा बनाया ना इसने इसके साथ बॉन्ड ब्रिज स्ट्रक्चर बनाने के लिए, ये एक्चुअल में बॉन्ड नहीं है, अदरवाइज ये BeCl4 बोलते हैं हम इसको, these Cl2 belong to the other beryllium, ठीक है ना। तो these are also known as electron deficient compounds. What are electron deficient compounds? जिनके पास इलेक्ट्रॉन कम होते हैं, अगर इलेक्ट्रॉन्स कम है तो they can act as a Lewis acid or a Lewis base. According to Lewis concept, जो इलेक्ट्रॉन्स देता है वो बेस, जो इलेक्ट्रॉन्स लेता है वो एसिड, तो अगर BeCl2 के पास कम इलेक्ट्रॉन्स हैं तो वो लेना पसंद करेगा या देना, लेना, तो it will act as a Lewis acid. Okay, that's another concept. All right, let's quickly talk about some important compounds. Here, see, the important compounds are, you have limestone. Limestone is what, calcium carbonate. So what happens on heating calcium carbonate? You form what, you tell me, what happens on heating calcium carbonate? That's limestone, CaO plus CO2. CO is a white amorphous solid, all right. फिर CaO, ये आपको पता है कि what is this? This is limestone. Limestone is actually forming CaOH twice, which is lime. Limestone is CaCO3. CaOH twice is basically your lime. No, it's forming calcium oxide and, I'm sorry. So this will form CaO plus CO2, all right. Now this CaO, when it reacts with water, will form CaOH twice. So then this will form CaOH twice. So the addition of, let me tell you, addition of limited amount of water to actually, the addition of limited amount of water breaks the lump of lime, which is known as slaking of lime. Ek minute, let me just tell you, this is quicklime, and then you have CaO plus CO2 again forming what? This you know will be forming your CaCO3. Remember that your calcium oxide, which is quicklime, is basically going to react with silica to form calcium silicate. Silica is your SiO2. It reacts with silica to form CaSiO3. And basically it is a basic oxide. Remember, quicklime is a basic oxide, and you have basic oxide है, तो basically it can react with acidic oxides. और हमारे acidic oxides जितने भी P block वाले oxides होते हैं ना, वो acidic होते हैं, जितने भी S block वाले oxides होते हैं वो generally basic होते हैं. So because calcium oxide, which is your quicklime, it is quicklime, and because it's a basic oxide, it can react with acidic oxides. So in this case it is forming CaSiO3, and here it will form calcium phosphate. So you will have the formula as Ca3PO4 whole twice. I hope you don't expect me to put down all the formulae here. And remember that calcium, the addition of limited amount of water to quicklime is generally known as slaking of lime, which is the formation of CaOH twice. Alright, then you can talk about its uses also. You know many uses of what, calcium oxide or quicklime. There are different uses of quicklime. What is your quicklime? CaO. What is lime water? It is CaOH twice. What is your limestone? It is CaCO3. So basically you should be knowing about that. It is used in the cementing and building for building purposes and all, and you can talk about the rest also. It is used in the manufacture of sodium carbonate also, caustic soda, from caustic soda. Alright, then we talk about slaked lime. Your slaked lime is what? What was your quicklime? CaO. Quicklime was CaO. Slaked lime is CaOH twice. कैसे बना? By slaking of lime. Slaking of lime मतलब पानी ऐड करा to quick lime, तो आपका बना slake lime. Alright, and then you know that what will happen if CaOH twice reacts with carbon dioxide. I am not going to tell you, these are very simple reactions. Alright, what will happen if CaCO3 then reacts with carbon dioxide plus water? What will be formed? Calcium carbonate plus water. इस केस में you will get back your limestone CaCO3 और कोई possibility ही नहीं है. So you will get your CaCO3 plus water. What about this case? Here your bicarbonate will be formed. So you will have CaHCO3 whole twice. ये तो formula है. Then you have यहाँ पे CaCO3 plus water. All right. यहाँ पे. All right. Then you have, if you take your slaked lime and react it with chlorine. This reaction is important because इससे bleaching powder बनता है. ठीक है? When you add chlorine to slaked lime, what you get is bleaching powder. So in this case, what you get is calcium chloride plus your bleaching powder, which is CaO2Cl2 plus H2O. वो भी है. Heavy. All right, so done with it. So I mean, just remember these are some very simple reactions that you do not have to be worried about, something that you already know. All right, next acha, if you talk about now the say if you talk about the uses, agar मान लो subjective paper में you get uses of calcium hydroxide or slaked lime, then in that case one of the uses is it's used for the preparation of bleaching powder. ठीक है, the other uses of slaked lime can be it is also used for the preparation of limestone. So such kind of uses that you already know from the reactions can also be put apart from the ones that you can mug up. It is used as a building material again. It is used in whitewash also. Then when you talk about now limestone, I am not putting down the reaction for the formation of limestone. What is it? CaO plus CO2 is forming your CaCO3. Now you know another reaction, that is CaOH twice also. If you bubble carbon dioxide through calcium hydroxide, ये तो खुद ही सोच लो ना, कार्बन डाइऑक्साइड को अगर कैल्शियम हाइड्रोक्साइड स्लेक्ट लाइम पड़ा है उसमें कार्बन डाइऑक्साइड बबल करा दोगे तो अगेन यू विल गेट कैल्शियम कार्बोनेट, एंड अदरवाइज द सिंपलेस्ट रिएक्शन इज कैल्शियम ऑक्साइड प्लस carbon dioxide. That's also forming your limestone. All right, it is the only thing is that you can talk about the reaction of calcium carbonate with acids. Talk about the reaction of calcium carbonate with acids quickly and tell me what will be formed. Remember, there will be kind of a double displacement in this case. तो इसमें भी मुझे कुछ करने की ज़रूरत ही नहीं है. CaCl, CaCl2 plus H2CO3. वो तो it's just the balancing of the charges, as you know. So it will be CaCl2 plus H2CO3, and in the next case it will be CaSO4 plus H2CO3. And remember, your carbonic acid is what? Carbonic acid is nothing but carbon dioxide present in water. What is carbonic acid? H2CO3 is nothing but carbon dioxide present in water. So it can also further dissociate to give you H2O and CO2. So basically the reaction can also be written as CaCl2 plus water plus carbon dioxide. फिर यहाँ पे CaSO4 plus water plus carbon dioxide. The reaction actually is put like that only. Then what is this CaSO4? ये यहाँ पे CaSO4 बना. Remember that calcium sulfate generally, if it is present with half water of crystallization, it's called plaster of Paris. So that is CaSO4 half H2O. It is obtained from gypsum. Gypsum is a naturally occurring mineral that consists of your calcium. It is CaSO4 dot 2H2O. So it is formed from what? CaSO4 dot 2H2O. What is this? This is gypsum. What is this? Half H2O wala? Plaster of Paris. Not writing the reaction, you can form it on your own. Then the last thing is like, we've been talking of the building materials. So cement is an important building material, and let me tell you it has a mixture of the alkaline earth metal compounds. ठीक है, तो अगर कोई भी alkaline earth metal का compound अगर किसी ने बोला उसके mixture से क्या बनता है, you can get it from the question. So what is getting formed? Cement. So remember कि जो best cement known है ना, that has a name called Portland cement. तो cement की quality, just in case, I mean if you become an engineer, I mean kind of involved in the construction work and all, so you can always test the parameter or the quality of cement. How can you test it? Let me just tell you, the average composition, see the ratio of, देखो उसमें सिलिका होता है, alumina होता है, you have Al2O3, you have SiO2, you have Ca, you have Al2O3, Fe2O3 also. The best one is when you have the ratio of silica is to Al2O3, वो ratio होना चाहिए between 2.5 to 4, ठीक है, और the ratio of lime to the total oxides, oxides मतलब कौन कौन से, SiO2, Al2O3, Fe2O3, इनका अगर ratio should be as close as possible to 2. So then your cement is of a good quality. Alright, next we move on to the P block quickly. Alright, is this thing clear to everyone? So there are some important compounds that you can actually talk about. What is slaked lime? What is slaked lime? CaOH twice. What is plaster of Paris? Calcium sulfate dot half H2O. What is quicklime? What is limestone? What is gypsum? What should be the ratio of the ratio of calcium oxide with different oxides? The ratio of quicklime with different oxides, it should be around 2, or 2.5 to 4 will be for the ratio of silica and alumina. So that can be checked for the quality of cement, and you can of course talk about it. So by and large, the important things, let me just recapitulate. The important things now. Remember that for the alkaline earth metals, हमने नया क्या करा, फजान्स रूल तो पहले वाला था, उसके अंदर we studied that the properties actually can help us predict the melting point trend also. Greater the covalent character, lower will be the melting point. And covalent character can be judged by Fajan's rule, that is high size, a small size of cation, large size of anion with high charge density. High charge density जिसकी भी होगी उसका melting point हमारे पास कम होगा, क्योंकि high charge density का मतलब है covalent character will be more. So one thing is that, and the second thing that you can actually talk about is that if we are talking about the solubility also, that can also be related to the covalent character. पर अगर उसका कोई आइडिया नहीं है, and if you can talk about the solubility trends given, then you can talk about what? Hydration energy and lattice energy. Lattice energy, if it is more, then your compound will be insoluble, and if hydration energy is more, then it will be soluble. But दोनों का trend generally on going down the group, it decreases. क्योंकि जितना छोटा साइज होगा उतनी हाइड्रेशन एनर्जी ज़्यादा होगी और उतनी ही लैटिस एनर्जी ज़्यादा होगी. तो उस कंपैरिजन हमें ये करना है कि किसमें डिक्रीज ज़्यादा हो रहा है. इसका मतलब अगर सॉल्युबल है तो लैटिस एनर्जी बहुत जल्दी जल्दी डिप कर रही है और हाइड्रेशन एनर्जी बढ़ रही है, और अगर वो नहीं है और अगर इनसॉल्युबल ज़्यादा हो रहा है नीचे जाते टाइम, तो इसका मतलब लैटिस एनर्जी इज रैपिडली इंक्रीजिंग. इफ इट इज इनसॉल्युबल ज़्यादा तो लैटिस एनर्जी इज मोर. Lattice energy more to insoluble, hydration energy more to soluble. Then another thing that I taught you today is that for generally alkali and alkaline earth metals, you can find out the lattice energy using a formula. That formula is obtained from dash cycle, Born-Haber cycle. What is delta HF? Heat of formation, that is equal to SDIEU. You know the meanings of each of the terms, so you can easily make it out for any of the elements. Main thing is like lattice energy is the energy released or energy required? Energy released. Electron affinity is the energy released or energy required? Released. Alright, and if we are talking about electron affinity, that is the energy released, ionization energy required. Alright, तो ये चीजें अगर clear हैं तो बाकी सब चीजें would be like a cakewalk to you. And you know, अब तो इतना stoichiometry और balance पता है कि you can easily form the compounds. So you can apply some of your mind also to write down the answers even if you have not read them in the books. Alright, now let's move on quickly to the P block so that we get introduced to it. P block का first अभी हमने क्या करा था, क्या था वो? Tell me. बैंगन, आलू, बोरॉन, एल्यूमिनियम, गैलियम, इंडियम, थैलियम. ऑलराइट, अब इसमें बाकी सब ट्रेंड सेम है, आयनाइजेशन एनर्जी वैसा ही है, इलेक्ट्रॉन एफिनिटी कुछ बदला नहीं है. मतलब द ओनली थिंग दैट हैज चेंज्ड इज नाउ यू हैव एन इंट्रोडक्शन ऑफ अ पी ब्लॉक नाउ एंड द जनरल इलेक्ट्रॉनिक कॉन्फ़िगरेशन इज NS2 NP1. साइज का वही है, नीचे जाते टाइम इट विल गो ऑन इंक्रीजिंग, आयनाइजेशन एनर्जी विल गो ऑन डिक्रीजिंग. बट अब की बारी ऑक्सीडेशन स्टेट्स कौन कौन सी पॉसिबल हैं? व्हाट आर दी ऑक्सीडेशन स्टेट्स व्हिच आर पॉसिबल? +1, ठीक है, +1 भी पॉसिबल है ना, क्योंकि एक इलेक्ट्रॉन देगा तो S तो हमारा कंप्लीटली फिल्ड है. सो +1 इज वन ऑक्सीडेशन स्टेट व्हिच इज पॉसिबल एंड द अदर इज माइनस कितना, -5. व्हाट विल इट बी पॉसिबल? +3. वाई +3? क्योंकि एक तो +1 देके ये खुश होगा और दूसरा +3 देके खुश होगा, क्योंकि देन अगेन द आउटरमोस्ट इलेक्ट्रॉनिक कॉन्फ़िगरेशन वुड बी लाइक अ noble gas, similar to a noble gas. Is this thing again clear? Okay, now just carefully look at it. अब मैं एक नया कॉन्सेप्ट बता रही हूँ before ending the class. More or less बाकी सब सेम है. How can I find out? By giving you a test paper tomorrow from P block directly. S पढ़ लिया, S के कॉन्सेप्ट्स क्लियर हो गए. I could make out from the faces तो समझ आ रहा है. I hope looks are not deceiving. मतलब I hope they're like the same inside and here. But now what we'll do, I'll straight away give you questions. You try solving them in just about 15-20 minutes tomorrow in the morning, so that Saturday, next Saturday, all right, before we begin, so that a P block can be summarized. Any doubts that you have can be sent to me directly. All right, one important concept which was a little different, and maybe one or two may be there, which I'll just cover up in the next class. I'll take up both the P. We'll be having boron family and nitrogen carbon family. Boron family and carbon family, we'll take both the families together and have a nice get together. So here we have NS2 and NP1. What are the most stable oxidation states? You have +1 and +3. ये पता है ना क्यों +1 क्यों +3. अब इधर P block में ना एक नया रूल है, that's called an inert pair effect. All right? समझ लो, लिखने की जरूरत नहीं है. इनर्ट पेयर इफेक्ट, यू नो अबाउट द, यू मस्ट हैव हर्ड ऑफ इट. इनर्ट पेयर इफेक्ट होता है कि जैसे जैसे द साइज गोज ऑन इंक्रीजिंग एज वी गो डाउन द ग्रुप, देयर इज रिलक्टेंस ऑफ s इलेक्ट्रॉन्स टू टेक पार्ट इन बॉन्ड फॉर्मेशन. बॉन्ड फॉर्मेशन, बॉन्ड ही बनेगा ना जब +3 इलेक्ट्रॉन्स देगा, तो किसी को तो देगा बॉन्ड बनाने के लिए. दैट मीन्स व्हेन, व्हाट इज द मीनिंग ऑफ +3? इट्स फॉर्मिंग एन आयनिक बॉन्ड. व्हाट इज एन आयनिक बॉन्ड? व्हिच इज फॉर्म्ड बाय द कंप्लीट ट्रांसफर ऑफ इलेक्ट्रॉन्स. All right, that's clear. So what happens that now as we move down the group, there is reluctance of the s electrons to participate in the bond formation. What did I say? There is reluctance. That means they are not willing to form a bond. So which oxidation state? अगर इसमें s कह रहा है मैं बिल्कुल bond नहीं बनाऊंगा, so then in that case what is the possibility of the oxidation state? +1 only. फिर तो सिर्फ P ही जो भी करेगा करता रहता, क्या होगा P. So remember that the reluctance of the s electrons to take part in bond formation is termed as inert pair effect. What is the consequence? The consequence is that the lower oxidation state becomes more and more stable on going down the group. So if I talk about any compound which is having say TiCl or TiCl3, I mean if I give you that kind of a compound, which will be more stable for thallium case? It will be, right? So what we have is, in this case it will be TlCl3. I'm sorry, I was saying a wrong formula. So here in that case +1 oxidation state will be more stable, right? That's called inert pair effect, where the lower oxidation state will be more stable on going down the group. That's clear? Now let's quickly talk about some more. We have another 2 minutes left and I can extend by another 2. So what we have, see, remember that you have thallium STL, and except boron all are metals. That thing is clear. Except boron all are metals, and boron will show its diagonal relationship to which element now? Carbon, silicon, germanium, tin, lead. You have here whatever, carbon, germanium, tin, lead. All right. अच्छा, अब इसका बता रही हूँ तो इसका भी बता देती हूँ. यहाँ पे सिर्फ boron is not a metal, whereas all the rest are metals. Here carbon is not a metal. These are basically acting as semiconductors, and नीचे वाले are metals. All right. In both the cases inert pair effect is predominant. यहाँ के oxidation states कौन-कौन से होंगे? ये second है P का. This is like the second group of the P block, and you have the fourth group otherwise. So what is the configuration? 1s2, 2s2, 2p2 for carbon. So it is ns2, np2. So what will be the oxidation states possible? Give me 2 stable oxidation states for this. +2 and +4. And which will be more stable on going down the group? Okay, carbon, silicon, germanium, you have tin and lead. So PbCl2 or PbCl4, which will be more stable? Because of inert pair effect. Alright, kahin pe bhi you have to, if you have to judge for an element which is located down the group, and you have to judge which element, which compound will be more stable for that, remember that the lower oxidation state will be more stable. So PbCl2 will be more stable. Alright, the diagonal relationship of boron will be similar to, will be with, the diagonal relationship will be with silicon. Alright, so we'll talk about that also. And remember that the hydride of boron is important, that is B2H6. Hydride of boron, boron is what? It is NS2 NP1. Boron is 5, right? So it will be 1s2, 2s2, 2p1. Alright, and it generally B2H6 means it is actually forming a compound. I talk about diborane later. It exists in the form of a diborane, which is twice of BH3. And here in case of ionization energy, how many ionization energies will you now be talking of in this case? IE1, IE2 and IE3. So if you talk about the ionization energy trends now, it will be a little difficult to actually make it out, because there will be a sharp, now let's, ionization energy 3, because we will just be looking for 3 plus. The most stable oxidation state otherwise iske liye generally is known to be 3 plus, because iska chloride banega AlCl3, BCl3, GaCl3 and so on. तो अगर हमारा most stable oxidation state है, that is ionization energy 1 plus 2 plus 3, क्योंकि +3 oxidation state बनाने के लिए तीनों ionization energies को add करना पड़ेगा. So that will be like a summation of all the 3 ionization energies. अब एक चीज और, एक तो inert pair effect बताया, वो समझ में आ गया. दूसरा ये है कि जब हम अब down the group जाएंगे ना, तो boron to aluminium हमारा ionization energy should, what should happen to ionization energy on going down the group? It should decrease. सिर्फ atomic size ही तो increase होता है, बाकी properties तो decrease ही हो रही होती है generally. तो your ionization energy will decrease significantly. लेकिन गैलियम, इंडियम, थैलियम में जब हम नीचे जाते हैं तो वो जो डिक्रीज होता है ना, दैट इज नॉट दैट सिग्निफिकेंट, इतना डिफरेंट नहीं होता. व्हाई इज दैट सो? बिकॉज मैं बताती हूँ, यहाँ पे हमारा S है, यहाँ पे हमारा P है, ठीक है, कुछ कुछ वर्ड्स याद है, वेरी गुड. सो यहाँ पे हमारा S है, यहाँ पे हमारा P है, ठीक है, बीच में क्या आ गया हमारा, क्या है ये, डी ब्लॉक. ऑलराइट, तो अब क्या हो रहा है कि जब हमारे पास बोरॉन, एल्यूमिनियम, गैलियम जब हम इनके पास आते हैं तो इनके अंदर D and F ऑर्बिटल्स आर आल्सो गेटिंग फिल्ड अप. इन दोनों केसेस में पूरे पूरे D फिल्ड हैं, इस केस में D और F दोनों फिल्ड हैं. तो अब क्या हुआ है कि आयनाइजेशन एनर्जी इज द एनर्जी रिक्वायर्ड टू रिमूव एन इलेक्ट्रॉन. तो जैसे जैसे हम नीचे जा रहे हैं तो इलेक्ट्रॉन की पकड़ तो न्यूक्लियस से कम होती जानी चाहिए, तो आयनाइजेशन एनर्जी शुड डिक्रीज ताकि हम आराम से रिमूव कर लें. पर होता क्या है कि जब D आ गया ना इलेक्ट्रॉन्स बीच में, तो जो D इलेक्ट्रॉन्स होते हैं दे आर वेरी पुअर शील्डिंग. मैंने बताया था शील्डिंग क्या होती है, जो इंटरैक्ट नहीं करने दे रहे, आउटर मोस्ट इलेक्ट्रॉन को न्यूक्लियस के साथ इंटरैक्ट नहीं करने देंगे बिकॉज दे आर शील्डिंग द न्यूक्लियस. मतलब एक शील्ड बना के बैठे हैं कि नहीं, वी वोंट अलाउ यू टू इंटरैक्ट विद द न्यूक्लियस. सो अगर उनकी पुअर शील्डिंग है, दैट मीन्स द न्यूक्लियस कैन नाउ होल्ड द आउटर मोस्ट इलेक्ट्रॉन अ लिटिल मोर टाइटली देन इज एक्सपेक्टेड. And if it holds it a little more tightly, then in that case the ionization energy would not be as low, but it will become a little higher. क्योंकि अगर उस बाहर वाले इलेक्ट्रॉन को, तो D, because D and F are poorly shielding, alright, the shielding effect is the highest in case of S, क्योंकि S सबसे ज़्यादा strongly bonded होता है, followed by P, followed by D, followed by F. तो जब D आ गया बीच में, now because D electrons are poorly shielding, so because of that the ionization energy decrease would not be that significant, because अब हमें energy ideally कम होनी चाहिए थी to remove, क्योंकि इतने सारे इलेक्ट्रॉन्स आ गए बीच में, वो आराम से हटेगा, रिपेल हो रहा है इतने सारे इलेक्ट्रॉन से, बट बिकॉज दे आर पुअरली शील्डिंग, वो न्यूक्लियर चार्ज को अच्छे से कवर नहीं कर पा रहा, तो न्यूक्लियस विल इंटरैक्ट विद द आउटर मोस्ट इलेक्ट्रॉन टू होल्ड इट मोर टाइटली. तो आयनाइजेशन एनर्जी रिक्वायर्ड वुड बी अ लिटिल मोर देन एक्सपेक्टेड. तो डिक्रीज उतना नहीं होगा जितना एक्सपेक्टेड है. डिक्रीज है लेकिन इन दोनों में सिग्निफिकेंट डिक्रीज है, लेकिन और नीचे जाते टाइम डिक्रीज इन आयनाइजेशन एनर्जी इज वेरी मिनिमल. क्लियर विद दिस? और इन दोनों में D पूरे पूरे फील्ड है, इसमें F भी आ गया, F तो और भी ज़्यादा पुअरली शील्डिंग है, तो इसीलिए देन द आयनाइजेशन एनर्जीज कुछ कुछ केसेस में P में देखोगी का कंपेरेबल है. So making use of that D-F relationship, inert pair effect also, I think these should be sufficient to understand your P block, apart from the other concepts of ionization energy, electron affinity and your hybridization concepts. Alright, if you have any doubts you can get back to me. All the best.